Okay, so today we're just going to keep working at 5.4, keep talking about exponential growth and decay. We're going to have a little bit more focus on some applications of this. So just to warm up today, we're asked to identify each of the following as an example of growth or decay and explain how we know. We'll just kind of talk that out. And then we're asked, what is the y-intercept? So in A, we have y equals 3 times 4 to the power of x. So why don't you just think in your head, would that be growth or decay? Well, that would be growth. The reason it's growth is because this value that's being raised to the power of x is bigger than 1. So basically you're multiplying by 4 each time. So as x gets bigger, you're going to keep multiplying by 4 and by 4 and by 4. Now the y-intercept, as we've done this in other types of functions, the y-intercept is, if we kind of look at this graphically, it's where we cross the y-axis, which is what is the y value when x is 0. So to find the y-intercept, we plug 0 in for x. 3 times 4 to the power of 0. Well, if you do 3 to the power of 0 in your calculator, you just get 1. So this is just 3 times 1, and we just get 3. So the y-intercept as an ordered pair is 0, 3. Let's look at this next one. Y equals 11 times 0.75 to the power of x. That is growth or decay, growth or decay. Because it's a number less than 1, it is going to be decay. To find the y-intercept, we just plug 0 in again. We can do this a little faster this time because if we just plug in 0 here, we know this whole piece goes to 1, so we just get 11. So our y-intercept is the point 0, 11. In part C, we're not given an equation straight up, we're given a situation. You saved $2,000 into a college savings account for 4 years. The account pays 6% interest annually. Is that growth or decay? Well, it's a college savings account, so it's growing. So your equation would look something like y equals our initial value times 1 plus 6%, which is like 1.06 to the power of x. And sure, it's 4 years, so we could plug 4 in, but for this particular problem, I mean, we're just asked to say whether it's growth or decay. This is growth. The y-intercept is just that number out in front, so that is indeed just 2,000. 0, 2,000. Okay, so to take these applications a little bit further, we did this a little bit in the last video, but here's just a great way to look at exponential growth or decay as it pertains to percentages. So this could be plus or minus r. If it's minus r, that's your percent. That would give you a value here less than 1. A is your initial amount. T, or x sometimes we use, is your number of time periods. So suppose you want to invest $500 in a savings account that pays 3.5% annual interest. How much will be in the account after 5 years? Well, we can write our function. A of t is equal to, A is our initial amount, which would be 500, times the quantity 1 plus 3.5%. That's 1.035. And then we're taking that to the t power. But for our case here, we already have the number. So let's just find what A of 5 is. So the amount in the account after 5 years is equal to whatever this is. So you can do this in a calculator. 500 times 1.035 to the power of 5 gives you 593.84. And that would be dollars. So turns out after just 5 years, you've almost gained an extra $100, which is a pretty good deal if you ask me. Let's look at another type of problem. You probably remember this from Algebra 2, but we call this our APERT formula. This is just a different way to calculate interest, and this is where interest isn't growing per year, but it's actually accumulating continuously. So for continuously compounded interest, that means the interest, it's always going up. We use this APERT formula where A is the amount in the account at time t, P is the principal, that's your starting amount. Rate is your interest rate in terms of your annual interest rate. This is calculating continuously, and T is the time in years. The piece that you maybe have forgotten is this letter E. Now, the letter E is kind of like pi. It's an irrational number. E is used mainly for continuously compounded interest, but it also has other applications in higher math courses. But for most of our purposes, we just use E. So I'm not going to get in this video, I'll get into a big, long discussion about where E comes from or anything like that. But just know that it's a really useful number. The decimal for it is 2.7182, and then I can't remember what it is. But it's like pi, so it would go on for forever with no end. So you're going to use this anytime you see the words compounded continuously or continuously compounded. So suppose you won a contest at the start of 9th grade that deposited $4,000 in an account that pays 5% annual interest compounded continuously. There are those two words. How much will be in the account when you enter college? So once you recognize compounded continuously, you know to use A/PERT. So A is equal to our principal, which is $4,000, times E to the power of 0.05 is our rate, 0.05 times 4. So when you do this in the calculator, you're going to do 4,000 times E to the power of 0.05 times 4. Go ahead and close your parentheses, and you get 4,885.61. So you gained about $800, almost $1,000 actually, if we're really going to round up, in just those 4 years. Pretty cool. Last thing we're going to talk about in this video is half-life problems. Once again, you probably remember these from Algebra 2 as well. This is more used in like a science context. So this is where different substances decay at different rates, and we call that a half-life, how long it takes for the substance to become a half of what it used to be. So your formula here is just your initial amount of the substance times 1/2, that's the half-life, times time over the half-life of the particular substance. So this is basically better explained with an example. A certain radioactive element has a half-life of 250 years. There are 42 grams of the element. Currently, how many grams of the element will remain after 462 years? So those are our 3 pieces of info. So the amount we have left, or the final amount of the substance, is equal to the initial amount, which is 42, times 1/2, to the power of time over the half-life. So we would do 462 over 250. We can put that into our calculator, 42 times 0.5 to the power of 462 divided by 250. When you're doing this in the calculator, make sure that you're raising this in parentheses. And we get 11.67 grams of the substance. So really not a whole lot left. But what this is actually saying is every 250 years, this amount gets cut in half. So if this was just 250, our number here would be 41, or excuse me, 21. But we're going another, 232 years, so almost another half-life. Half of 21 is 10.5, so it's only down to 11.67, but that's the idea, that every 250 years, there is half of that substance left over. So your homework tonight is to work on the application worksheet that I have posted on Schoology. So it's a bunch of problems basically using these 3 ideas. Most of them will just use this. So just be careful if it's growth or decay. So if it's appreciating, it's growth. If it's depreciating, it's decay. So please work on those problems for the next time we meet.